Now, if you have dropped the coin, to find the coin, you just have to walk towards this road. Now, when you have a playground which is of the dimension 100 feet by 200 feet, can you find that coin easily? In this video, we are going to talk about one of the dimensionality reduction technique, that is PCA, that is principal component analysis. In machine learning, it's good at some point that when we have more data, but after some time, the machine learning model performs it actually starts performing worse as the volume of the data increases. Now, as the number of features increases in my machine learning model, the number of dimension actually causes the decrease in the model's accuracy, because at that time I'll have to have a task of generalizing huge volumes of data set. And this is actually known as the curse of dimensionality. Now, to illustrate the curse of dimensionality, let's say that you have a coin. Okay, so let's say that you have a coin and you have dropped this coin. Let's assume that in a road. Okay, you have dropped this coin in a road. Now this road, let's say the road looks something like this. Okay, you can think of it as just a road which is having, I would say, 0.5 feet in width, and this road is having, I would say, a length of, let's say, 100 feet. Now if you have dropped the coin where the width is 0.5 feet and length is 100 feet, so what you have to do is, to find the coin, you just have to walk towards this space, or you just have to walk towards this road from one direction to the another direction, and there is a very high chance that you are going to find the coin, because you just go straight by looking out for the coin. So that's the easier scenario. Now imagine that you have lost the coin, but not on a road, but on a football field. So you've got a football field. Let's say football's field dimension is 100 feet by, let's assume, 200 feet as an example. Now when you have a playground which is of the dimension 100 feet by 200 feet, can you find that coin easily? No, it's not possible, isn't it? Well, that example is to show you the importance and the curse of this dimensionality that we generally have in machine learning. That's the curse of dimensionality. See, as the number of dimensions in my data set increases, it's very difficult for the machine learning model to generalize the data set. So that's where the concept of dimensionality reduction comes into picture. Now, when we talk about this dimensionality reduction, so here there are various ways in performing this dimensionality reduction. So what exactly is this dimensionality reduction? Let's first define it. So dimensionality reduction is a technique to reduce the number of features in my data set. So here, during the feature engineering and the exploratory data analysis, we have already seen as how we can reduce the number of features. Well, we can reduce the number of features by removing the unnecessary columns, taking care of missing values, and remove the duplicate columns. I mean, these are the straightforward ways in reducing the number of columns in my data set. Now, this is a straightforward way. Now, let's consider a scenario. Okay, let's say I've got a data set. Okay, so this is an Excel sheet that I've got. Now, in this Excel sheet, let us consider that I've got 3 columns in my data set. So I've got height, weight, okay, and I also have the information about age, and based on this I have actually the BMI. Okay, let's do one thing. I have the height, weight, and age. Okay, and I have the prediction column. Let's say I want to predict whether the person is diabetic or not. Okay, so I have 4 columns in my data set. So the first 3 columns are the features, or nothing but the input, and the last column is the target that I have got. Okay, now when I say dimensionality reduction, it is about reduction of number of columns in my data set. Now in this scenario, we clearly have 4 columns in our data set. Okay, I want to reduce the number of columns. Now, if you look closely, the column of height, weight, and age. See these three columns that you see right here. See these three columns. Yes, these three columns can actually be combined into a single column, isn't it? So I can combine these three columns into a single column. So how can I combine these three columns into a single column? Well, with my basic knowledge, I can say that, hey, instead of using height, weight, and age of my individual person, I can combine it and represent all these three columns into a single column of BMI, so that these three individual columns that I have got, I can now transform it into a new column called BMI and represent the values in terms of BMI instead of using three different columns, that is height, weight, and age. And the last column, I'll keep it as it is. So what happened in this example is I have reduced the number of dimensions from 3 to 1 by applying this technique. Now, what is the technique? Well, I have applied the technique of my domain knowledge, and using my domain knowledge, I have reduced the number of dimension. So it's very easy as it sounds, but the problem is it gets challenging when you start working in a different domains. Let's say as a data scientist, you are someone who is from the computer engineering background and you know nothing about the medical domain. Now at that time, when you have been given with the medical related data set, how do you reduce the data? Because you don't know about the domain knowledge that is there in that medical domain. I mean, you may get the basic knowledge, but you'll not be in a position to reduce the number of features using the technical terms, isn't it? Well, that means what we need is we need a methodology which will help us in reducing the number of dimensions without having us worrying about the domain knowledge that is actually required. Well, that's where the mathematical methodology comes into picture. So the mathematical methodology that we can use it is a principal component analysis methodology. So using this principal component analysis methodology, we can actually compress the data set into a lower dimensional feature subspace with the goal of maintaining the most relevant information. Okay, that is the overall idea about this principal component analysis. Now, if I want to describe this principal component analysis technique, well, principal component analysis technique comes under the unsupervised linear transformation technique, and this is generally used across the different fields. And most prominently, this principal component analysis is used in feature extraction as well as dimensionality reduction. So it is used in these two applications. So feature extraction and the dimensionality reduction. Now the other popular application of this PCA would include EDA, that is exploratory data analysis, and denoising of noise signals in the stock market trading, and the analysis of the genome data and gene expression levels in the field of bioinformatics. So these are some of the applications of this principal component analysis. So overall, this technique of PCA helps us to identify the patterns in the data set based on the correlation between the features. As an overall, I would say that this would aim to find the directions of maximum variance in a high dimensional data and projects it into a new subspace with equal or fewer dimension than my original data set. To get an illustrated understanding, let's consider the example. Let's say I've got a data set. Okay, I've got a data set that looks something like this. So I have the data points that looks to be like this. Now when I have a data point that looks to be like this, as you can clearly see in this data set, I've got two features right here. See, I've got two features in this given data set. Now what we are trying to achieve is we are trying to achieve by reducing these two features into one feature. Now that's the outcome when I say that dimensionality reduction. But when we talk about this PCA, what would happen is we are interested in generating the principal components. These principal components are also known as orthogonal axes. So these are the orthogonal axes of the new subspace. So these green lines that I'm drawing right now, these are all the principal components. I'll call this as PC1 and PC2. These are the two principal components that I have drawn. And here the idea is each principal component gives or explains the maximum possible variance in a given data set along that particular axis. Now in this figure, the x1 and x2 are my original feature axis, that is my original features. And this PC1 and PC2, these are all the principal components that I have actually created. Now, if I make use of this PCA for this dimensionality reduction, what we generally do is we are going to construct a D by K dimensional transformation matrix W. Okay, we are going to construct D by K dimensional transformation matrix W, and this allows us to map a sample vector X into a new K dimensional feature subspace that has a very few dimensions than my original D dimension feature space. So as a result of transforming my original D dimensional data into this new K dimensional subspace, typically this value of K will be less than D. So the first principal component will have the largest possible variance, and all the consequent principal components will have the largest variance given the constraint that these components are uncorrelated, that is they are orthogonal to each other. That means my PC1 will be greater than PC2, greater than PC3, and so on. So that is how we interpret the principal components. Now, some of the key factors that you need to remember from the examination perspective is this technique of PCA is highly sensitive to the scaling of the data set. So ensure that before you apply the PCA, ensure that you scale the data. So we have to first standardize the features before we apply this PCA. If the features were measured on different scales, this is one of the very important steps because we want to assign equal importance to all the features. Now, when we talk about this PCA for dimensionality reduction, so if I want to describe the high level steps, so what we do is, first thing that we will do is we are going to standardize d-dimensional data. Now, once I perform the data standardization, I'm going to construct covariance matrix. Now, this is followed by decomposition of the covariance matrix into eigenvectors and eigenvalues. And then I'm going to select k eigenvalues. Okay, I'm going to select the k eigenvectors. Okay, it's actually the eigenvectors. I'm going to select k eigenvectors which k largest eigenvalues. So what I'll do is, before this step, I'll actually sort my eigenvalues. Okay, I'm going to sort the eigenvalues, and this is followed by selecting the k eigenvectors. Now, once that is done, we are going to construct the projection matrix. Okay, we are going to construct the projection matrix. I'll say W from top k eigenvectors. Okay, so in this way, we are going to implement this PCA, that is principal component analysis, on a given data set. Next, in order to implement this in a hands-on manner, we'll take up two approaches. First approach is I'll show you in a mathematical way, because that is important as a data scientist that you to remember this PCA technique. And at the end, I'll also show you the methodology of scikit-learn library. So let's go ahead and implement this so that you're going to master this technique, because these are all the application level questions that you would expect in the examination. It's very important that you understand it in a practical way. You don't need to code it in the examination, but you need to know and you need to build an intuition to answer the tricky questions that you would experience in the examination. So from sklearn dot model selection, I'm going to import train test split, and from sklearn dot pre-processing, I'm going to import standard scaler. Okay, now once that is done, I'm also going to import NumPy library as well. Okay, once I've done the necessary import, what I'll do is I'll start by reading the data as a data frame. Okay, so the data set that I'll be using is a wine data set from the UCI machine learning. Okay, so from the UCI machine learning website, I'll be loading the data set. So let me try to load the data. So this file that I've got is the wine.csv file. So I'm going to load this CSV file. Okay, so I'll say data, that is df wine, is equal to pd dot read underscore csv, and I'm going to specify the file name, that is wine.csv, and I'll display the first few rows of this data frame. So this is how the first few rows of my data frame would look like. So I'll display the shape of my data frame. So I now have 14 columns in my data set and 178 rows on this given data set. Okay, now what I'm going to do is I'll just separate the x and y from this given data set. So I'm going to say x is equal to df wine dot drop, and I'm going to say columns is equal to, okay, let's do one thing. So I'm going to consider the column y, that is wine, as the output. So I'll say df wine drop columns is equal to wine, and I'll say y is equal to df wine, and I'll assign the column of wine for y. Okay, in this way I'll be separating the x and y. Now once I separate this x and y, so the next thing that I'll do is I'm going to split the data set into two parts. I'm going to say xtrain comma xtest, ytrain comma ytest is equal to train test split. I'll mention my data, that is x comma y comma test size is equal to 0.3, and I'm going to say stratify is equal to y, so that we can create a stratified split. And I'm also going to specify my random state, and this is equal to, so for the demonstration I'll mention it as 20. Okay, or we'll keep it as 0. Okay, in this way I'll split the data into two parts. Now once I've split the data, let's apply the standard scaler on this given data set. I'm going to say ss is equal to standard scaler, and I'll say xtrain std is equal to ss dot fit underscore transform, and I'll apply it on my xtrain. Then I'll say xtest std is equal to ss dot fit underscore xs got just transform, okay, ss dot transform, and I'll apply my xtest. So in this way we'll apply the pre-processing on this given data set, and this is a mandatory step while performing the analysis, that is the PCA analysis. Now let's go to the next step. See, the next step is we have to construct a covariance matrix. The symmetric d by d, that is the, let's say if I have got the dimension d dimension, the d by d dimensional covariance matrix is what we have to construct, where d is the number of dimensions in the data set, and it would actually store the pairwise covariance between the various features. Okay, so let's go ahead and create the covariance matrix, and then we will go ahead and get the eigenvectors and the eigenvalues. So in order to find the covariance on my feature data, I'll start by generating my covariance matrix. I'll say cov underscore mat is equal to np.cov, and here I'm going to specify my data set, that is xtrain. Okay, that's how we'll have to specify the data. Now once I've generated, if I display the dimension of this COV, see I've generated the matrix of the shape 13 by 13. So this is a covariance matrix. Now from this covariance matrix, I'm going to generate the eigenvectors and eigenvalues. So I'll say eigenvalues, comma, eigenvectors is equal to np dot linear algebra dot eig. Okay, and inside the parenthesis I'll have to specify my covariance matrix. So this is going to generate my eigenvectors and eigenvalues. So np.cav function will generate me a covariance matrix, and here this has yielded me, the eig function has yielded me an eigenvalue and the eigenvector. Okay, so here if I display my eigenvalues, so this eigenvalues has 13 values over here. Okay, and if you look into the eigenvectors, so these are all the various eigenvectors that I have generated. And if you look into the eigenvalues, okay, so here the eigenvalues look something like this. Now whenever we are working, okay, so we generally refer this eigenvalues which defines the magnitude of the eigenvectors. So what we generally do is we have to sort these eigenvalues by a decreasing magnitude, and we'll be interested in top k eigenvectors based on the values of their corresponding eigenvalues. Okay, now apart from this, okay, we also want to ensure that, so we have to understand the variance explained ratio using this eigenvalues. Now the variance explained ratio of this eigenvalue is simply a fraction of eigenvalue and the total sum of the eigenvalues. That means if I use that individual eigenvector, how much variance can I explain from this given data? Okay, so in order to calculate the cumulative sum of explained variance, so this is how I'll be writing the code. Here I have mentioned as sum of eigenvalues, okay, which is my sum, and var underscore exp. Okay, so variance explainability is equal to I by total for I in sorted eigenvalues comma reversed is equal to true. Now once I've generated the value, we'll just go ahead and create a plot. So if I create a plot, this is how it would look like. So once I create the plot by referring this explained variance ratio, this is how the plot would look like. So this resulting plot indicates that the first principal component actually accounts for closer to 35% of variance in my data set. I would say closer to 40% of variance. And we can also see that by combining the first two principal components, so we can explain closer to 60% of the variance in the data set. Now if I make use of, let's say, 4, okay, with the 4 features itself, I can explain closer to 80% of variance in my data set. Okay, now once we have successfully decomposed the value, that is once I have decomposed my covariance matrix into the eigenpairs, now we can now proceed ahead with the last few steps of PCA, that is to transform my existing data set on top of this new principal component axis. So first I'm going to sort the eigenpairs by descending order of the eigenvalues, and then I'm going to construct the projection matrix from the selected eigenvectors. Now to demonstrate this is how I'll be writing the code. So here in this code, so I have sorted the eigenpairs by a descending order of the eigenvalues, and we have constructed the projection matrix from the selected eigenvectors and use the projection matrix to transform the data into the low dimensional space. So this is the matrix W that we have got. Okay, now if I want to generate the lower dimensional space representation, what I can do is I can simply say extrain std, okay, get an individual row, and if I perform the dot product with W, okay, this is actually my W. See, this is going to generate my data in 2 dimension. Okay, so this is how I can reduce the number of dimensions. So what I have done in this scenario is I have manually shown you as how we can perform the principal component analysis for a given data set. Now we don't have to build the wheel from scratch each and every time that we are doing it. So the idea is we can make use of the PCA algorithm which is present inside this scikit-learn library. So I can directly say that from sklearn.decomposition, I'm going to import PCA. I'll say PCA is equal to PCA n components is equal to 2. And here, once I have initialized the object of PCA, I'm going to say xtrain PCA is equal to PCA dot fit underscore transform. I'm going to apply my xtrain std. Okay. Then I'm going to go ahead and display my xtrain PCA. So if I display my xtrain PCA, this is how it would look like. Now just observe the first value over here, 2.38 and 0.54. We have the similar value. Only difference is we have the difference in scale, but that is fine. Here it is in negative, this is positive, but the overall vector representation is same. So which means that whatever the manual approach that we have used to reduce the number of dimensions to 2 from 13 features, if I implement it with the help of scikit-learn library, we can also do the same as well. So the principal component analysis is one of the most widely used technique when it comes to the reduction of dimension. If you want to understand the explained variance ratio for each and every plot, maybe you can just initialize the PCA without number of components, and after that you can get the explained variance ratio, and on top of this I'm going to call np.cumulative sum. If I execute it, see, it just describes the overall explained variance ratio. So if I use 3 features, I can explain closer to 70% of variance in the data. And if I use 5 features, I can actually explain 81% of the variance that I've got in the data set. So what it means is, here, instead of using all the columns, if I just make use of first 5 principal components, by reducing the number of dimension, I can still explain 81% of the variance in the data set. Now, this might not be an ideal for this case, but imagine a scenario where you have got thousands of columns in the data set. Now, in such scenarios, you would definitely agree to use just 100 rows instead of 1000 rows if it is giving you 80% of the variance in the given data, assuming that your model and the system is not capable of handling the 1000 columns. So at that time, instead of lagging and instead of just waiting and seeing the system crash, you can just reduce the number of dimensions and use that data in implementing the machine learning algorithm, which will help you to proceed further in the problem statement. Okay team, so this was about the dimensionality reduction technique, that is PCA. So PCA is a technique which will help us in reducing the number of dimensions in a mathematical way. To do this, first we will generate the covariance matrix, and then we are going to apply the eigen function to generate the eigenvectors and eigenvalues. Now using those eigenvectors and eigenvalues, we will generate the principal components. So we can also look into the principal components as well by calling the components attribute. So these are all the principal components that I have generated for this given data. Okay, so thank you so much guys for staying with me till the end, and I'll see you in the next video where we will look into the another methodology of dimensionality reduction, that is LDA, that is linear discriminant analysis. So I'll see you next time.